Hi, welcome to the problem solving session. So, I'll do a quick recap of what we had done last time. So, I hope you're able to see the screen and so on. So, last time we saw this model called DFA, which is defined as which is formally defined as a five tuple Q sigma delta Q0 and F, where Q is the set of states, sigma is the alphabet, then delta is the transition function, and Q0 is the start state, and F is the set of final states. We also saw that a language that is accepted by a DFA are called regular languages. Now in this week, we're going to look at the slightly different model, which is called non-deterministic finite automata. Okay. And this is also formally defined as a five tuple Q sigma delta Q0 and F. And the key difference between a DFA and an NFA is that your transition function somehow is slightly more, at least it appears that way, that it's slightly more powerful. So now we've defined, so for DFAs we had that delta is a function from Q cross sigma to Q. So if you are at some state and you see and you read a symbol, then it tells you where to go. Now for NFAs we've defined this delta to be, okay, I'm audible, right? Can one of you please confirm in the chat? Okay, thanks, Tanvi. So so you've defined this transition function to be Q cross sigma to the power set of Q. So instead of going to a single state, your transition function can now go to a set of states. So it can happen that, say, you are at a particular state Q0 and you read a 0. So in case of DFA, there's only one unique possible answer. In this case, you can go to Q1, you can stay at Q0, and there could be multiple such options. So that's the only difference that we have in the model so far. So this week we'll look into we'll get comfortable with the definition of NFAs, and we'll try to see whether this seemingly powerful model, is it really as powerful? Is it really more powerful than DFA, or is it just the same? So so this week we'll take a look into this, and let's start with the simple question. Okay. Okay, I'll just try to get this diagram on the other page. Just give me a moment. Okay, maybe I'll just erase this one. Okay. So yeah, sorry about the. Okay, so you have this NFA that is given to you, and this question asks you to write the transition table corresponding to it. So what we mean by that is on. Okay, right. So you are at. Okay, so you are at state Q, which is say Q0, and the alphabet that we're working with is 0 and 1. So if you are at Q0 and you see a 0, what are the states that you go into? So basically this captures our function delta, which is Q cross sigma to the power set of Q. So yeah, so like can you can any of you tell me what should the answer, what should be the entry in this particular table? So if you are at Q0 and if you are at Q0 and you see a 0, what should be the um, the set of states that you can reach? Maybe I'll show you the diagram. Okay, right. So as Tanmay has answered correctly, so if you are at Q0, indeed you can reach Q0, that is pertaining to this transition, or you can reach Q3, which is because of this transition that you have. So I'll write here, you can go to Q0 or you can get to Q3. Now if you are at Q0 and you see a 1, there's only one possible transition here. So yeah, so you'll only end up at Q0. Now let's say you are at Q1, and I would encourage you to maybe like can you like write in the chat box what should I write for Q1 0 and Q1 on 1? Yeah. Sorry, do you mean Q0 and Q1 for? So if you are at 1, you can either get to Q0, or if you read a 1, you can get to Q1. I think that's what you probably. Right. Okay, sorry. I'm really sorry. Okay, so if you are at Q1 and you see a 0, there is no possible transition. So the set that so you really, there's no state that you can reach to, and that's what the empty set denotes. And if you are at Q1, then there's only one possible transition here, which is at Q2. Now similarly, if I'm at Q2 and I see a 0, uh, okay, I'll be like writing this here, but in the meantime, I would really appreciate if you could write your answers, whatever you have come up with in the chat box. It just gives me an idea of where the understanding of the class is. So if you are at Q2 and you see a 0, there's only one transition. Sorry. Yeah, there's no transition, so you get to free. And if you are at Q2, you see a 1. This transition takes you back to Q1. This transition takes you to Q4. So there are two possible states that you can reach. If you are at Q3 and you see a 0, then there are two possible transitions that we have here. One that takes you to Q4 and the other that takes you to Q2. And if you read a 1, there is no transition, so I'll write phi. Now, if you are at Q4 and you see a 0 or 1, then there's only one possible state that it can go to, that's only Q4. So for Q4 we have Q4. So I think, as you can see, the key difference with NFA is that in case of NFA, when we wrote the transition table, here you do not have an option to write multiple possible states, and NFA gives you that power. So I hope this question is like a good recap of what the NFA model is. Yeah. And like, if there are any questions, please feel free to ask. So we'll look at the next.
Can you explain again for the previous one?
Yeah. Which one do you want me to? Which state? Doubt in Q0.
Yes.
Okay. So if you are at Q0, then on reading 0, there is one transition on 0 that takes you to Q0. So we have Q0 in the set. And there is this other transition that takes you to Q3. So we have Q3 in the set. And there is no other state that you can reach by reading 0. So yeah, this is okay. And okay, I get it. Thanks for pointing out. You're saying for 1, there are two possible transitions. One is Q0 and Q1. Okay, thanks.
Yes.
Okay. Okay. Right. So, yeah. So moving to the next question, you have been given an NFA, and okay, maybe I'll quickly recap what a computation tree is. So let me just quickly draw a sample NFA. Okay, so this is my NFA, and let's say I want to read the string, and say this is my final state. So let's say I want to read the string AAAB. So what does a computation tree do? It basically tells you what are the states that you can reach when you on the NFA. So in case of DFA, there's only a unique state that you can go to. So if you see a 0, let's say you start at Q0 and you see an A, there's only one state, say Q prime, that you reach to. Then if you read the next state, there's only one possible state that you can reach to. So if you read a string of length n, you get a path of length n plus 1, and it's unique because every transition is fixed. But in case of NFA, there are so many possibilities, and the computation tree basically captures what all possibilities are there. So let's take an example. Right. So let's say you are at Q0, because that's the start state, and you read A. So there are two possible states that you can reach to, which is, this is exactly what we did in the previous question. We saw if you are in a certain state and you read a certain alphabet, then what are the states that you reach to? So if you see an A, if you see an A, either you can reach to Q1 or you can reach to Q2. So this A is visited. Now for the next A, if you are at Q1, there's only one possible transition that you can make, which is to Q0. Which is to Q0. And if you are at Q2, there is no transition that is possible. So this branch is terminated. You can't explore this further. Okay. And yeah, let's say you are in Q0 now and you have one more A to read. So from Q0, if you have A, then you have two branches. One is that takes you to Q1 and the other that takes you to Q2. Now you've read three symbols here and the only symbol that you need to read is B. So if you are at Q1, there is no transition that is possible. So again, this branch will be pruned. And if you are at Q2, there is a transition that takes you to B. So you simply stay at B. And because and you simply stay at Q2. And can like someone tell me whether this string A B will be accepted by this NFA?
It is accepted by the NFA.
Yeah,
Accept.
good. Thank you. Yeah, good. So because there is these are the possible I mean the possible endings that you can get if you go across any path, and since Q2 is one of those possible states which you can reach and Q2 is a final state, so A B will be accepted. Now I'll just erase. Okay, so now this question asks you to compute, to draw the computation tree on each of the following strings, and based on that, you want to tell whether the string is accepted or not. So I'll just wait for, I'll wait for a minute, and I would like to see your answers in the chat, and then we can discuss. Okay, so okay, so um, let's look at A. So you start at Q1 and there is simply no transition from Q1 on A. So this thing will so in the start itself this will get rejected. So A is not accepted. I hope like you.
This
Okay.
Q1 will be final state, no? Or it will be start state.
Q1 is
If we go,
both the final state as well as the start state.
but it is double circle, no? So it will be it should be final state.
So it should be, sorry, what?
It
Can you
is double
repeat?
circle.
Right,
Q1.
but Right, but you are at Q1 and when you see A, there is no
If
transition,
we
right?
if we start from Q3 and then go to QA, then
But your start state is fixed, no? Like, um, you have a unique start state, right? So no matter what, you're going to start at Q1 only. And that, I mean, do you agree with me on that?
okay. Because like in our college it was told that for double circled it is a final state, and here both final and start state are the same.
Yeah. So is that the confusion that start and final state cannot be the same? Is that what you're saying? Or
I had that doubt.
yeah, it is perfectly fine for, I mean, you can have the start state to be same as the final state. So for example, you might have seen this simple DFA, right?
Yes.
Yeah, so in the language accepted by this is sigma start. And in this case, there's only one state, which is the start as well as the final state. So it doesn't
Okay.
contradict with the definition of the five tuple, so it's fine. I hope
Okay.
that answers it.
Yes.
So, right. So in this case, you have the Q1 as your start state, and on reading A, there is simply no transition. So A will not be accepted. Now let's look at B. Again, you are at Q1, you see B. There's only one transition here, which is to Q2. Then you see an A. Now you have two possibilities, which is either you stay at Q2 or you go to Q3. Then you have one more A to read. If you are at Q2, again you have two possibilities. Either you stay at Q2 or you go to Q3. If you are at Q3, there's only one possible transition, that is to Q1. So the set of states that are reachable uh, is Q1, Q2, Q3, and one of this is a final state. So BAA will be accepted. I hope that is okay. So I'll move on to C. So you start at Q1 and again you see B. There's only one state that you can go to, which is Q2. Now you see an A. On A, there are two possibilities, that you stay at Q2 or you go to Q3. Now there is B, A, B, B, A. So we have read B, A. We need to read a B. So if you are at Q2, you go to Q3 on B. And if you are at Q3, there is no transition. So this is already uh, pruned. Now we have to read a B. So from Q, yeah. So from Q3, again, sorry. Yeah, again there is no transition that you can make to Q from Q3 on reading a B. So there is no possible path that we can explore now. The only two paths we had are both pruned, so this will not be accepted. And like for the last one, uh, can you like answer, would it be accepted or not?
The last one is accepted.
Yeah, correct. So I'll leave it for you as an exercise. It's quite similar to what we did so far. So, but if there are any doubts, you can. I'll wait for a sec. For some time, you can ask. Okay. So we'll move on to the next question. Okay, just a second. I just want to make sure whether this is getting recorded or not. Okay, this is being recorded. Like also, I just wanted to check with you all. So the last week video and the PDF of this problem set that we're discussing, this has been shared. I hope you're able to access it. Okay, like if not, then let me know anytime. So yeah, so in this question, you are given some regular languages and you want to design an NFA for these languages. So like I'll wait for a minute for you to try and then we'll look into the answers. Okay. So let's start with A. So you have this language which consists of all the strings which end with, maybe I'll write this as W00, where W in sigma star. So this is the language that and we want to design an NFA for this. So let's say like you start at Q0. Okay, like so far, even in the case of DFAs, what we've been doing is we're appealing to the intuition and we intuitively design the NFA by like sort of trial and error. But there is a mechanical process where like there's a set of instructions that you can follow, which if the language is regular, you'll be able to come up with a DFA, which you will be seeing later on in the course. But for now, because we're not introduced to it, we'll intuitively sort of try to come up with the machine. So you are at Q0, and if you read a 0, let's say you go to we'll write this as Q, and this is Q0. Then if you read a 0, let's say you go to Q00. Okay, so we don't want to read anything after Q00 because we want the string to end with it. So we'll make it a final state. And now if you are at Q, you're sort of waiting until you reach the near end of the string. So if you are at Q, you keep on waiting. Once you get the second last what do you say, like second last element of the string, you go to Q0 if it's a 0, and when you read the last element of the string, if it's a 0, you go to Q00. So my claim is that this is so note that because this is an NFA, you don't need to draw transitions for every possible state on every possible alphabet. So my claim is that this is indeed accepting the language L. Like, does any of you has any? Have any counter thoughts or something?
Ma'am, can you explain again how
Oh,
you wrote the expression for L? I have
okay.
doubt on that.
Yeah, sure, sure. So, yeah. So L is the set of all the strings that end with 00, right? So what we're saying is, I mean, every x that has 00 at the end should be accepted, and we don't care what is before that. So let me write W as whatever is there, I mean, there could be lots of strings that end with 00, and I'm simply calling them as X. And they could be anything, right? I mean, it could as well be epsilon, uh, in which case this is just the string that you have is just 00, and
Yes.
right.
Uh,
And
and after that, I've written in W.
in
So
sigma
what is
star,
that?
oh, okay,
Ah,
this
yes.
this is my 01 star, because sigma is 01. uh, is this star is what is creating an
No,
issue?
the whole equation, like we have written W belongs to 01 star. What does that mean?
Okay, so that means every possible string that you can, right, so you agree, right? What we're capturing by all the strings here is anything that you can, uh, anything
Yes.
over 01. So this, we want to capture every possible string over 01. So, okay, like, so if S is maybe, right, if sigma is 01, then you know sigma 0 is, I mean, just epsilon, right?
Yes.
And sigma 1 would be 01. Then sigma 2 would be 00011011, and you go on doing
Yes.
this. So sigma star is defined as sigma 0 union sigma 1 union and so on. So this is basically every possible string that you can generate.
Okay.
Okay, so
So
that's
if it
what,
is written sigma star, then it means all the possible
all
combinations
possible.
with zero and one.
Correct, yeah.
Okay.
Okay,
And W means that it belongs to that the
that,
string belongs contains only zero and one.
sorry, I didn't catch that. W in,
Like if it is in W belongs to zero sigma star, then it means that whatever contains only contains zero and one.
yeah. So sigma star is the set of all possible strings that you can have over, right? This is what it would look
Uh,
like. And when I say
yes.
W in sigma star, I mean it could be any of these elements. It could be any one of them.
Okay.
It's some string over 01.
Okay.
Okay, good. So yeah. So does anybody have like, I mean, any questions about whether this is really the correct NFA, or I mean, is there any doubt? Okay. So, okay, maybe I'll just do a trial run on few strings so that if there is any doubt, I mean, you kind of convinced. So, so let me start with 00. This is the smallest string in L. So if you are at Q and you see a 0, then one of the paths will take you to Q0. And once you are at Q0 and you want to read the second 0, there is a path to Q00. So you can get to Q00. Let's say you have 101 and we don't want, maybe let's say 1010, we don't want this string to be accepted. So what Q would do is, you start at Q, you see a 1, there's only one transition, that is you stay here. Then you see a 0, on 0 you go to Q0, there is no choice. Okay, sorry, you have, yeah, you have two choices, either you go to Q0 or you go to Q. Then you see a 1, and at Q you have to stay at Q. If you are at Q0, there is no choice, so you kind of prune it. And yeah, and now you have to read a 0. So on 0 you could go to Q or you could go to Q0, but none of this is an accepting state, because the final state is only Q00. So these kinds of strings would not be accepted. And I mean, I hope it is clear. Okay. So maybe when we look at the other two examples, I hope things will be okay. Right. So just just one point that I want to say about this is the question here explicitly asks you to draw an NFA with three states. And there's nothing specific about that. You could have an NFA with four states, five states. I mean, depends on the language that you have. But I think with this particular case, you can't get lesser than three. So three is kind of the minimum states that you need. So like even if you have doubts about this, these things will come up later. So I mean in the later part of the course. But okay, just want to like give you a heads up. So
Then can you
the
show with 5 states the previous one?
okay, so for every language, you may not. Uh, you may not be. I mean, if you give me some number, say five, and you give me some language L, it may not be possible to always have. I mean, have an NFA for that language with those many states. I'm just saying that there could be multiple NFAs, but if you like okay, but like if you like what forcibly if you want to make it five state, then you could like add dummy states that are not reachable. Um, as in, let's say this is Q4 or whatever, and this is Q5, and there are transitions like this, but this is a
Like
part
it is not possible for this question. We can
not
see that.
not possible as in.
Like it is for this question we can draw only 3 states.
No, like for example, I'm giving you this. Okay, this is very cluttered, but okay. So this is my Q4, this is my Q5, and let's say I go on 0, 1. All this is 0, 1. Okay, 0, 1, 0, 1, and so on. Is it visible? Do you want me to draw this again?
No, ma'am, visible.
Huh. So right. So what I'm saying is forcibly you can always do that. So in this case what I've done is I've added Q4, Q5 which have transitions like this, and the language is not changed because Q4 and Q5 are not even reachable.
Yes, ma'am, understood.
Right. So if you have n state DFAs, you can all DFA or NFA, you can always make n plus 1, n plus 2, and so on. uh, I mean those this is just one way of doing it, which is by adding dummy states, but sometimes you might have like seen this while practicing, that you're given a language, you may come up with a DFA, and you for that language, your friend may come up with another DFA for that language. Those two DFAs may be very different, but they could still be recognizing the same language. So that's what I meant. That there's nothing specific about three, but three is the minimum that you have and that you need. And in the later part of the course, maybe when you learn the tools, you can maybe go about proving why three is minimum that you need. But right now, that's not the focus for now. But later, when we come to it, we can talk about it. Okay, I hope that was clear. So now for the B part, you have a simple language which just accepts 0, and you want to design an NFA. So what you do is you are at Q0, and if you read a 0, let's say you stay there, and okay, sorry. Right, you can't do this with one state. I think you can maybe like do trial and error and see you can't do with one state. So when I wrote a 0 here, it actually, if you read 0, you would end up at Q0. But if you read 0, 0, you would still end up at Q0. So if you are accepting on 0, you would end up accepting on 0, and you would end up accepting on any number of zeros. So this is not what we want. So what we want is, we want to remember that we have seen 1, 0 exactly. So let's say my Q1 state tells me that you have exactly read 1, 0. And now I want to accept here. Okay, and I think you don't really need any transition, because if you do this, you would end up accepting 0 plus, which is 0 0 0 0 0 and 0 0 0 and so on. We don't want that. So this loop would be, yeah, this loop is not required. And yeah, because this is an NFA, you don't need to give a transition on 0, I mean on Q1. But if it were a DFA, then maybe you can have a dead state here for accepting the same language. Like, is that clear? Okay, thanks. So next language that you have is, I'll add one more page. Right. So the next language that you have is 01 union. Just a minute. Yeah. So you want to design an, okay, I hope like this language is clear what we mean by union. Okay, so maybe I'll just give you a few examples. So what we mean is, if you see, if I were to write just 01 union 010 union 001, what I mean is L contains 01, it contains 010, it contains 001. And when I do a star operation over here, what we mean is you take one of these, any one of these. Let's say I take 01. Okay. Okay, like if, right. So you take any one of these, then concatenate it with any one of these. So let's say 010, and concatenate it with again any one of these, and you can do it any number of times. I mean, you could do it once or twice, or say as many times as you want, and the resultant string would be in L. So let me just show you what L would look like. So it contains, these are the elements that you get by not concatenating anything at all. And also like epsilon would be in here, because because a star means you can choose any one of them at most like 0, at least 0 times. So then if you choose two strings, you would get something like 0101 or 01010, 01001, and so on. So I hope like the language is clear. If not, please ask. Okay, so I'll break this. I mean, we'll construct the NFA, but I'll break this problem into smaller pieces. So we'll design smaller NFAs first, and then we'll sort of like use these ideas to construct NFA for the language L that we are interested in. So let's say my L prime is simply 01 star, and what would the NFA look like? So you are at Q0, which is, let's say, your start state, and um, okay, if you see a 0, you go to Q1, and if you see a 1, you come back to Q0, and I make Q0 to be the final state, so that once you see 0 and you go back on seeing a 1, you end up accepting it. Also note that because Q0 is the initial state, epsilon would be in the language, would be accepted by this NFA. So this language basically looks like, sorry, L prime looks like epsilon 01 0101, then 010101, and so on. So I hope this is clear. Right. Now, if you look at the language, there are like three parts that you have. There are three strings. So for maybe let's say L double prime is your 010 star. Then what would the NFA look like? Let's say you are at P0, then you see a 0, you get to P1, you see a 1, you go to P2. Now when you see a 0, let's say you come back to P0. And I want this to be my final state because on reading 010, I end up at P0 and I want to accept it. So what does L double prime look like? Okay, maybe I'll just write it. So this accepts epsilon because start state is itself final. Then it accepts 010. It accepts 010 followed by 010 because once you get to P0, you can again see if you see another round of 010, again you would go P1, P2, and P0. So you would end up accepting strings like this 010, 010, 010, and so on. So if you break this L into smaller parts, you know how to make a NFA for them. Now we just want to join them together so that all together it captures our language L. So okay, I'll take a new page. Okay. So you are at Q0, let's say, and you see a 0. I'm just basically drawing this NFA for L prime. So if you see a 0, you go to Q1. If you see a 1, you come back. So this part is taking care of the 0-1 language. Now if you see, now I want to take care of this part. So if you see a 0, you go to Q2. If you see another 0, if you go to see another 0, you go to Q3. And if you see a 1, you come back to Q1. So this second loop that I have is taking care of the 001 part. And for 010, I'll again do the same thing. If you see a 0, you go to Q4. If you see a 1, you go to Q5. If you see a 0 again, you come back. Now, note that, let's say, so what we've basically intuitively done is we've taken all these three NFAs for each of these and we've combined them, like merged the start state of them. So what happens is if you have a string like this 01, so like can one of you tell me whether this should be accepted by the NFA or not?
It should be accepted.
Yeah, so correct. So how would this NFA go about it? It will like sort of intuitively imagine to be broken into three chunks like this, where 01 is from this set, 001 is again from this set, and 01 is from this state. So what it does is you are at Q0, then on 0 you go to Q1, then on 1 you come back to Q0. So in one round of Q001, you've kind of come back, you came back to Q0. Now if you read 001, there is a second loop that will process 001 and take you back to Q0 again. So your state goes like Q1, Q0, then it goes to Q2, goes to Q3, and again come back to Q0. Now you've read this part of the string and you're at Q0. Now if you see a 01, you again go to Q1, again come back to Q0. So because this is the final state, you would end up accepting. And so intuitively what this is doing is it's sort of breaking your string into chunks like this. And for each of the chunks, there is a way to read and come back to the start state. So this NFA would end up accepting exactly this language. Right. So, like as an exercise, you can maybe like offline, you can try to design a DFA for the same language. It may not be like very straightforward. In this case, you just like what we did is we simply intuitively built these blocks and we joined them together such that it accepts the language that we want. You can also get a DFA, but it may not be like it may not be very. It could be a bit tricky. You can get it, but it could be tricky. So like as an exercise, you can try to do it offline. So one reason why we are interested in NFAs is that it's intuitively very easy to make transitions without worrying about the possibility of going to multiple states. So in this case, like if you are at Q0, there are so many transitions that are possible. Q1, you can go to Q2, you can go to Q4. uh, but it gives you this flexibility to design your NFAs, that you don't need to worry that your NFA is kind of like not going to a unique path. And so that's the only that's intuitively why we introduced this model of NFAs, because it's easy to capture your languages that way. So okay. Okay. So you might have just a right. So there is a way for you to okay, like first of all, let me ask a simple question. Like is every DFA by default an NFA also?
Yes.
Right. Uh, Good. So you know that for every DFA uh, is by default an NFA. But if you have an NFA that say recognizes a language L, can you have a corresponding? So maybe let's say there is N, and what L of N denotes is the language. This is basically the set of strings W is accepted by NFA N. So machine N, let's say. So this is called the language of the machine, which could be DFA, NFA, whatever. So let's say that you have an NFAN and L of N is the language accepted by it. So what this theorem says is that there is a okay. Is that for every NFA, let's say N, there is a DFA, let's say D, such that the language of N is the same as language of D. So that means if you're given an NFA, you should be able to come up with a DFA which accepts the same language. So it could be that this DFA is very large in terms of the number of states, and it could have very different transitions. You don't change the alphabet ever because you want to recognize the same language. So your sigma would remain constant, Q would be different, your set of final states, your initial state, everything else could be different for this DFA, but sigma remains the same. So so in this sense, we say that NFAs are as powerful as DFAs, even though it has this extra, extra capability to jump to a lot of states on one transition. But in terms of languages, whatever is recognized by an NFA is also recognized by a DFA. So in that sense, we say that they're of the same power, and it's up to you whether, depending on a problem, whichever is convenient for you. Sometimes it's very easy to come up with an NFA, while it may be very daunting to come up with a DFA. So I mean, because of this theorem, it's like if you're asked to show that a language is regular or something, you can, I mean, whichever is convenient for you, you can either give an NFA for it or you can give a DFA for it. Yeah, so doesn't matter. So in this question, you're asked to, you're given this NFA and you want to construct a DFA for the same. So one way to, like one very, I mean, trivial way to, I mean, like naive way to do that would be that you look at the NFA, you come up with the language that the NFA recognizes, and then you try to build a DFA uh, for that language. That is one way. But there's also a mechanical sort of like a step-by-step procedure that helps you convert any NFA to sorry that helps you convert any NFA to a DFA. So you might have seen this method called subset construction. Method. So yeah, in this question, we're going to practice this subset construction method. So I'll try to get this image here. Right. So yeah. So what we'll do is we'll again break this process into small steps. So the first question that we started with today is that you were given an NFA and you were asked to write the transition table for the same. So that's what we're going to do. So let's say you are at A and you read a 0, then you can you can go to A or you can go to B. If you see a 1, you stay at A. If you are at okay, sorry, what? Okay, yeah. If you are at AB, right. So what are the possible states that you can reach to? So if you are at A and you see a 0, you can go to A, you can go to B. And if you are at B and you see a 0, there's no transition that is there. So if you take union of these states, that would be AB. So from AB, if you see a 0, you end up at AB. Is this okay? Is this step okay? Okay. Thank you. So yeah, now let's do, if this is clear, can you answer me what should be the entry over here?
ABC.
Correct. So okay, one second. I mean, I think you won't go to B, right? If you are at A and you see a 1, you only go to A. And if you're at B and you see a 1, you go to C. So you don't get B in this case. Is that fine?
This can you explain again?
Sorry?
Can you explain again?
Yeah. So you are in this A or B state. And if you are at A, you see a 1, you only go to A. Correct? You can only reach A because there is no transition for B.
So A, comma B state means we have to consider both 0 and 1.
Ex- Not 0 and 1. No, you're writing only for alphabet 1.
So alphabet 1 for A or for B or for both.
Yeah, for both. You take union. So first you do for A, you will get some states. Then you do for B, you get some states. you take a union of both the sets.
Okay.
Okay, so in case of A, you can only reach to A because you have only one transition that takes you to A. And if you are at B and you see a 1, you go to C. Correct. So union of these two would be AC. Is this fine with everyone? If not, like please ask me again.
Yes, but how do we reach to B? From A to B it is 0, no?
From A to B it's 0. No, so what this means is if you are in A or B and you see a 1, what do you where do you reach?
Only till A. If we are at A, then we only reach till A.
Yeah, if you are in A, then you only reach in A. So you agree on this part, on the left part.
Yes.
And if you are in B, where do you go? On
C.
seeing a 1, C. So what is the union of these two? AC.
But then how do we reach from A to B when it is 1?
No, you cannot reach.
So why do we write here EC?
Yeah, so you just write AC. It is also possible sometimes in some cases, I don't know for this, I mean, in this NFA, whether we're going to come up with such a case, but it's possible that, let's say, you are here, or maybe let's say, like, you are in some states, and it's possible that you just don't reach anywhere. That is a possibility. So, I mean, um, I hope like intuitively what this is capturing is that fine with everyone? So, like, when we draw this computation tree, right? um, what we're doing is we're looking at all possible uh, states that you can end up in if you read a particular string. So this is also kind of capturing the same thing. If you are at A or B, and you read one, where all can you, like, what all possible states can you end up in? So maybe like we'll do the other examples, and I mean the other entries, and if there are any questions, please ask. Okay, so what I'm doing here is I'm not, or maybe, okay, let's do for this one first slowly. So can you write in the, you can unmute or you can write in the chat what should be the entry for this?
ACD for
ACD.
1.
Okay, correct. No. Can you think again? Like, can you take a
It,
minute? Sorry, I didn't catch you if you said anything.
it is ACD when it is 1. For 0, it will be again A. No?
Yeah, that is right. So for 0, you have AB, because if you are at A and you see a 0, then you can go to A or B. If you are at C and you see a 0, then you go to A. So the union of this is simply AB. So that's what we have written here. And in case of 1, I need some space. Okay. So in case of 1, if you are at A and you see a 1, you go to B. If you are at C and you see a 1, then you go to D. Those are the only possibilities. So union of this is B comma D. So I'll write, yeah.
Means we can reach again A no? In this case when it is 1.
we can again reach A.
It is loop, no, it is 0, comma 1 at A. So it will be both A.
Okay, correct, correct. Sorry. Yeah. So if you read an A, you get to A. Correct. Yeah. So, okay. So what I'm doing over here is we simply okay, this color is visible. So we simply started with our start state, which is A. Then we wrote the transitions for this. And if we see any new subset, then we are writing it on the LHS. So I did not write a B after A because B didn't even show up here on the left hand side. So what this means is if you are at A, these are the two possible outcomes that you have. B is not even reachable at this point. So we simply pulled out AB and wrote the transitions for it. Now AB is already done. A is already done, which is is right here and AB is right here. AC is the new set that we got. So we pulled it again into the LHS and we wrote the transitions, the possible transitions here, AB and AT. And now there is a new set that that we've discovered. So we'll write it on the LHS and do the transitions for it. So if you are at A and you see a 0, you go to A or B. If you are at D and you see a 0, you stay at D. So this is what you get. And on 1, if you see, on A, if you see a 1, you stay at A. On D, if you see a 1, you either go to C or you stay at D. Hope this is okay. Okay. So now you have two new states these are the two new states that we did not account for on the left hand side. So we'll do the same process for each of them now. So if you are at A, B, D, and you see a 0, where do you go? So on A, if you see a 0, you go to A or you go to B. On B, there is no transition, so we don't have anything to add. But on D, you go to D. Let's do the same thing for 1. On A, if you see a 1, you stay at 1. On B, if you see a 1, you go to C. On D, if you see a 1, you either go to C or you go to D. So now, can you identify what should I write on the LHS now? What is the new set that we need to take care of?
A, C, C, D.
Right. So let's do ACD. So yeah. So on A, if you let me show the DFA. So on A, if you see a 0, you go to A or you go to B. On C, you go to, there's no, you go to A, which is already here. On D, you stay at D. Again, on A, if you see a 1, you stay at A. On C, if you see a 1, you go to D. On D, if you see a 1, you go to C or you go to D. Now, this one is already taken care of here. This one is the current row that we are in. Sorry, is the current row that we are in. Sorry, why did I write CC here? Okay, I just meant ACD. I think there is no new state, right? No new set that is introduced. So we can terminate this process. Is this step okay with everyone? Okay, so I hope like you can see why we are terminating this process here, because all the states that all the states that we had here are already exhausted. So they're already taken care of in one of these rows. So we don't need to continue the process, because you can, but it won't, it won't give you anything new. So now, yeah. So now we're going to make a DFA for this. So what I want you to see is that if each of this state, let's say my state set AB is associated with a state in a DFA, which is QAB, or let's say if the set is A, then I have associated QA. So for every set of alphabets, there is a set that takes care of it. So what would this transition table correspond to? If you interpret, yeah, if you interpret this as QAB, this as QA, and so on, can you tell, yeah, can you identify what does this give us? Like, does this correspond to something that you've already seen?
Ma'am, can you repeat?
Sorry, you want me to repeat?
Yes.
Yeah. So my question is, there is this table in front of you, and initially when we wrote this, you had a subset, right? Which was A comma B, A comma C, or something. What I'm saying is, for every subset, replace it with a state. Say for set QAB, let's replace it with QA comma B. QAB, and replace A with a state called QA, and so on. So this is QA. And what does that mean? If you are at QA, a state called QA, and you read a 0, you go to the state called QAB. If you are at QA and you see a 1, you go to a state called QA. So this is a transition table. So can you tell me whether this is a deterministic, this is table corresponding to a deterministic finite automaton, or is it something for a non-deterministic finite? Okay, so what I'll do is I'll draw uh, I'll draw the automaton corresponding to this, and
DFA,
then correct,
deterministic.
correct, good. So it is deterministic because for every state there is a unique state that you go to now. In case of NFA, it was non-deterministic because you had lot of possibilities, and now because we replaced every subset with a unique state, this is deterministic, because on any state, if you follow any transition, you would uniquely end up in one state only. So let me draw the right. So let's say you are at let's say you are at QA and you see a 0, then you go to QAB state. If you see a 1, you stay, sorry. If you see a 1, you stay at QA. Then take this QAB state. If you are at QAB, so like, can you tell where should I draw the arrow? On 0.
Okay, a loop at QAB.
Correct. It's a self loop at QAB. Then if you see a 1, it goes to a new state called QAC. And if you are at QAC, if you see a 0, it goes to QAB. If it sees a 1, it goes to QAD. Now you look at this AD. If it sees a 0, it goes to a new state called QABD. And if it sees a 1, it goes to a new state QACD. From ABD, now we are here. If you see a 0, you stay here. If you see a 1, you go here. And from ACD, if you see a 0, you come here. and if you see a 1, you stay here. Now we've drawn a finite automaton, but we've not yet identified the final state. So start state is clear, right? Start state is something that you, I mean, in this case, start state remains the same because A is what you started with. And yeah. Now, can you identify which states here should be the final states? So I'll show you the diagram. So
ACD.
okay, okay. So ACD is one of the correct answers. There are several other states that need to be finite. So can you maybe like think for a minute and tell me if there's something? Okay. Okay, so in case of computation tree, what we did is you have like you have lot of possible states that you can end up in, let's say. Then how do you decide whether the string is accepted or not? If it contains one of the final states. Right, other states is something we don't care about. So in this case also, if there is a subset that contains a final state, then we will make it an accepting state. So there could be multiple final states here. So for example, like you said, ACD should be a final state because it contains D, which is a final state in this automaton. And there are several other states also that contain D. So for example, this QAD, and I think yeah, that's all. So because uh, so let's say S is a subset of the states in your NFA, and if S contains some element in the final state, then you should make it S is a, okay, let me write this way. So S is a subset of the sets that you had for NFA. The subscript 10 tells you that it's an element from NFA. And if S has some has non-zero intersection with the final states, that is there is some final state that is contained in S, then S should be S's final state for DFA. So in this case, every subset that had a D in it would become a final state. So that would be QACD, AD, and ABD. So yeah, so this is indeed the DFA corresponding to the given NFA, and you can also offline you can maybe verify whether they are actually accepting the same languages. But this is a mechanical like step-by-step procedure which no matter what NFA you give me, I'll follow this procedure and I'll end up with a DFA. So are there any doubts about this entire subset construction process? If so, like this is a good time to ask. Okay, thanks. So I'll move on to the next question. Right. So you've given this NFA, and what I want you to do is you have four options, and each of these options correspond to a regular language. You want to tell which is the correct language corresponding to an NF, corresponding to the given NFA. So I'll wait for a minute and I would really like to see your answers in the chat. Okay, so yeah, so like Tanmay, your answer is almost correct. So as in one part of it is correct. So it does indeed accept those W's that contain at least two zeros. So you can see that from the first part of the, I mean, from the top part of the NFA. So epsilon transition basically just means even if you don't read even if you don't read anything, you could be in Q0 or you could be in Q1. So okay, so you will see more of this later in the course, but for now, just take it for granted that on seeing epsilon, you are basically free to jump to that state. So now, if you see at least if you see at least two zeros, then then you would end up accepting. So you could be reading more zeros from here or here, doesn't matter, but you should be reading at least two. So this part takes care of the so this part will accept all the strings that have at least two zeros. Now for the second part, note that there is a small difference here. In Q5, you don't have a transition on one. So 111, for example, if you do a test run, so can you tell me whether the string 111 would be accepted?
Just one doubt.
Yeah,
Like it is at Q0 it is given epsilon. So if we are using for 111, so can we go for the upper one?
yeah. So okay, let's try. That's a good question. So you are at Q0 because of the epsilon move. You could as well be in Q1. Now if you see a one, yeah. Now if you see a one, Q1 can take you to Q4, and sorry, Q0 can take you to Q4, and Q1 can take you to Q1 itself. Okay. Now you've read the first one and you want to read the second one. So if you are here, Q4 will take you to Q5 on reading a 1. And where does Q1 take you? Q1 makes you stay at Q1. Now you've read two ones and you're going to read the last one. So if you are at Q5, there is no transition on 1, right? It only has a transition defined on 0. So this will not take you to any state. So we will remove this branch. Let's look at Q1. Where does Q1 take you? If you see the third one, it takes you to Q1 only. And Q1 is not a final state. So in either case, you would not end up accepting 111. Because like even if you take this epsilon branch, on 111 you would only end up in Q1. There is no other transition that allows you to move to some other state. Okay. I hope that answers. So, right. So, the correct answer should be C, which is that it contains at least two zeros or exactly two ones. And the difference is, I mean, the only difference in the two things is that in one it is at least, in the other is exactly. This is because on Q3 you have a transition on zero that takes you to Q3. So even if you have read 0, 0 and you have entered Q3, if there are more zeros that are coming up, you will still end up in the same state. But in case of Q5, if you have seen two ones, you are at Q5, but there is no transition that is defined on one. So, yeah, if you see one more instance of one, you would not be accepting it. So that's the only difference that I wanted you to notice.
Ma'am,
Yeah, sure.
like if we consider if Q2 repeats 5 times in the loop, then it would be more than one. It would be more than two. No? One will occur more than 2 times.
Q1 repeats one more than two times.
Like if we start from Q2 and go to Q1, then Q1 repeats 2 times, then Q1 goes to Q2 still. Q1 repeats 2 times again. So in that condition, there will be more than one in the string. No? So that is also possible. Like it contains both 0 and 1.
Uh,
So the number of count of ones can be more. No?
so what is the string that you are reading? Can you tell me? I'll write it for the sake. What is the string that you want me to read?
Like Q0 goes to Q1.
Q0 goes to Q1 on reading, okay, epsilon. Then,
Then Q1 repeats 2 times itself in the loop.
okay, so you are
One
reading
one.
1, 1. Okay,
One. Then
Q1,
Q1 goes to Q2.
Q1 goes to Q2
Ah,
on reading a 0.
yes. Then Q2 goes to Q2 itself 2 times on reading 1.
Q2 goes to Q2 itself two times on reading 1. Okay. Okay.
Then it goes to Q3.
On reading a 0.
Yes. Then Q3 again goes to Q3 on reading
On
1.
reading ones, okay. So you read 0 and then you read bunch of ones, doesn't matter. So you would end up
Yes.
accepting this string. That is correct. So you're not accepting it because it has two ones, exactly two ones. You're accepting it because you have read at least two zeros. So there are two conditions here. Either you accept because you have read at least two zeros, or you accept because you have read at least two ones. So in this case, you're accepting it because you have read at least two zeros.
Okay.
Okay, that's a good question. Okay. So yeah, if there are no doubts, I'll move on to the next question. Um, yeah. So you're given that L is a regular language, and so L complement is something. Let me define. So let's say L is 0, 0, 0, or okay, let me say that is a set of all strings which are of odd length. Okay, so 0, 1, 0, 0, 1, 0, and so on. So basically, L is the set of all W such that W is of odd length. Now, L complement is defined to be everything that is not in L. So if, say, sigma star is the set of all possible strings that you can have, then L lies somewhere here. Then L complement is everything in this shaded region. Is that is this okay on the definition?
Yes.
So can someone tell me in words what should I write for L complement? Just like we wrote for L in terms of this.
W is not in sigma star. We can write W.
Yeah, like we defined in words that L is the set of all strings which are of odd length. Can you describe in words what is L bar? So what should I write? W is of even length, right? Because any string would have either an odd length or an even length. So herein you have all the odd length strings. So where should the even length strings lie? It should definitely lie outside. So I hope this is okay. Okay, sure. So can you answer if L is, so L is regular because there is some NFA or some DFA that corresponds to L. So should there be a DFA or NFA corresponding to L bar as well?
No,
Can you please repeat? I didn't catch.
no, it should be not regular
Okay, why do you think so?
because all the regular languages of L were included in that set. So the remaining will not be regular. No?
Um, no, why should it
Like
be?
all the regular expressions for language L were included. So the remaining ones may not be regular.
Um, okay, I think I didn't quite understand why. Okay, why you think so? But I would like to listen. What if anybody else has something else to some other opinion? Or you could also use the chat. Okay, so my claim is that this is a L bar is a regular language. What I'll do is I'll show you. No matter what L is, which is no matter what regular language you give me, I'll give you an L bar. I'll give you a machine, DFA or NFA for L bar, and that machine will exactly recognize the language L bar. Now, if you have, like some of you may have questions. So maybe let me just go through it, and then if you have questions, please ask. So let's say that L is regular, so there must be some DFA, let's say M, such that the language of M is exactly L. So let's say that M is this 5 tuple Q sigma delta Q0 and F. Okay. Now my claim is that let's say uh, this is some DFA that you would have, and let's say there are some final states here. I don't care what the transitions are, I'm just abstractly drawing this. Now, my claim is what you do is you change, you define another M prime, which is Q sigma delta Q0. The only thing I'm changing is F. So, my state in the new machine, my set of states is the same, my alphabet is same, my start state is same, and transitions are same. Only thing I'm changing is the final states. So what I'm saying is f prime would be all the states. So basically, if in the initial DFA, if a state is final, in the new DFA you make it non-final. If in the initial one it's non-final, you make it final. So you're just flipping. Now my claim is that M prime would accept exactly language of M prime is exactly L complement. So why am I saying that? Intuition is that you process some string, take any string x in sigma star. Suppose it reaches a final state in M. Okay. Then M would accept it. Right. Now in M prime, what I have done, I've only made that final state to be non-final state. So what would happen when you read X? You would follow the same set of states. You would end up in this state some Q, but now it is a non-final state. So what would happen is is if X is accepted in M, then X is rejected in M prime. Is this clear? Is this first part clear?
Ma'am, can you repeat again from the start?
Yeah. So right. So you have this machine M, right? You have some machine M because L is regular. There has to be a machine, some DFA. Only thing I'm changing about that DFA is every non-final state has become a final state now, and every final state has become a non-final. So basically, I've swapped all the final and non-final states. Is this okay? Is the construction okay?
Yes.
Okay. So now my claim is you take some string, okay, and you run it in the DFA that you were given. It will end up in some state. Now that state can be a final state or it can be a non-final state. So let's do case by case. Let's take the first case. Suppose X reaches a final state in M, so it is accepted. Is that okay?
Yes.
Okay. But in the new machine that we modified, what did we do? We changed the non-final, the final state to non-final state.
Yes.
Okay, so maybe I'll draw this to make it a bit clear. So this is the M that you had. What you did is you started here, you followed a set of transitions on X, you ended up at this state. In M, it was a final state. Now what I did is in M prime, I simply made this a non-final state. Okay. So what will happen? In M, X is accepted. But what happens in M prime?
X is not accepted.
X is rejected, correct. Now let's take the other case. Other case is that you are at Q0 in M, you follow a transition on X, and you reach a non-final state. What will happen in M prime? So in M, X is rejected. But what will happen in M prime?
It is accepted.
Correct. So in M prime accepts X. So what happened is, no matter what X you take, if X is accepted, basically if X is accepted by M, then X is in L. Okay. Then X will not be will not be accepted in L bar, because this is simply what we did here. If X is accepted in M, X is rejected in M bar. That is what I'm writing. If X is accepted in M, that is X is in the language of M, then X is not in the language of L bar. Correct.
Yes.
And similarly, you can write it if X is not in the language of L, then X would be in the L bar. So what does that mean? Language of this M prime is everything other than the language of M itself. So whatever was accepted earlier would be rejected now. Whatever was rejected earlier would be accepted now. That is exactly what L bar was, right? Everything that is here is not here, and everything that is in L bar is not in L. So this is exactly capturing the complement. Is this fine with everyone? Okay, thank you. So in interest of time, maybe I'll skip the seventh question. We can take it later in the next tutorial, but I have a simpler, small, nice question for now. So, okay. So this question asks you, you have this alphabet, which is 0, 1, 2. What you want to do is you want to design a DFA with one state only. So the question is, how many such DFAs can you design? So maybe you can take a minute and you can write. Okay. So Tanmay, any guess?
8.
8. Okay. Why? What is your intuition?
Oh, ma'am, I have not studied the DFA topic, so I'm just guessing.
Okay. Okay. So
Can you explain,
yeah, sure,
like,
sure. So yeah, I'll let you complete. Yeah, what would we say?
uh, ma'am, I don't know the topic of DFA. So
Okay.
can you explain first?
Yeah,
Then
sure,
I
sure,
will try.
sure, sure. So right. So DFA is basically your five tuple, which is okay. Sorry, Q sigma delta Q0 and F. It is the tuple. I mean, everything is same as NFA. The only thing is that this transition function that you have, it takes one state, it reads a symbol, and it only takes you to one unique state. In case of NFA, what was happening is, for NFA you can read a state, you read a symbol, you can go to multiple possible states. For example, you are at Q0, you see a 0, you're allowed to do this in an NFA. You can go to Q0, you can go to Q1 and so on. But DFA doesn't allow you to do that. DFA simply says, I am in Q0, I read a 0, just tell me one state where I should be. It should be unique and there should be only one state. So therefore this difference on the RHS. Is that
Ma'am, can you repeat?
sure, sure. So you understand NFA, right?
Yes, ma'am.
So, what does NFA do? Let's say in this example, what does NFA do? You are at Q0, you see a 0, you can go to Q1, you can go to Q0. This is a valid NFA, right?
Yes.
But this is not a
Uh,
valid. Okay,
it doesn't contain final state for this.
yeah, that is fine. That is allowed. Your final state can be empty, or it can be
Okay.
everything. Anything is okay. So yeah, only thing. This is not a DFA. It is an NFA, but it is not a DFA because your DFA doesn't allow you to go to multiple states. So DFA would say that you are at Q0 and you see a 0, you just tell me one state where I should go. It won't allow you to do multiple possible transitions. That's the only difference. So that's why here you
Okay, so we can reach from one state to only
only
another
one
state.
state. Correct. That's the only difference.
Okay.
So what you will do is you have been given this one state only. The question gives you only one state, and uh, obviously that has to be the initial state because you don't have any other state which could be your initial state. On what DF
Yes.
is correct. Now what DFA says is if you read any symbols, you have to give me a state where I should be going, but there is no other state. So only possibility for you is you stay on the same state. Correct.
Yes.
Okay. Now what you can do is this state could be a final state or it could be a non-final state. If it's a so that is the only choice you have. So there are only two DFAs that you can make. This is your DFA 1 and this is your DFA 2 which has a final state. So I mean just as a follow-up question, can you tell me the language of DFA 1 and the language accepted by DFA 2?
Q will be it will contain 8 for non DFA.
No, sorry, I didn't understand what were you trying to answer?
Uh, for DFA 1 there was in DFA 2 there is a final state.
Correct. There could be
So
or
it
there
is
could not be. It is possible that
okay.
there is no final state. So that is what I'm saying. You have only two possible DFS. One is with the final state and the other is without final state.
Okay.
There are
Understood.
okay. So the answer is P. I was just saying, okay, I was just saying as a follow-up question that the language of this DFA is empty because it does not accept anything, because there is no final state. And the language of this DFA is 0, 1, 2 star, which is it accepts everything.
Yes, understood.
Correct. Now, now you have this another question. Instead of DFA, I'm asking you how many NFAs can you have with one state?
Means in this case, should it be 8?
Um, what is your reasoning for 8?
Because it was 2 raised to q.
2 raised to q as in?
In the previous slide you showed, no? Huh. That-
Okay, 2 raised to q as in it's not necessary that all the subsets should appear. It is possible that some subset doesn't even appear.
Okay.
So if you go by the same reasoning, I mean the same idea that
Again
we
2. It would
uh,
again be 2.
okay. Okay, let's see. So you have one state, right? And this has to be your initial state. There is no choice for that. Now, if you see a 0, like your NFA allows you to not have a transition at all. Like if you are at a state, you see a 0, there may or may not be a transition. So you have two choices. Either there is a transition on 0 or there is no transition on 0. Okay. So for sigma, for 0 itself, there are two choices. Either you can have a transition or you can not have a transition. If you have a transition, it has to be on itself because there is no other state. Similarly, you now look at now you look at 1. If you look at 1, it is possible that sorry, it is possible that it has a transition, in which case you will get this the in which case you will get this. If it doesn't have a transition on 1, you will get this. Am I making sense? I mean,
Miss, ma'am, can you repeat?
yeah. So first, this part you agree. So what I'm saying is, on 0, NFA allows you to make a transition, or there may not be a transition. So on 0, your NFA could do something like a self loop here, or it could not have any transition at all.
Yes.
Correct. Similarly, for 1, you have same choices. You could have a transition which is a self loop, or you could have no transition.
Okay.
Correct. Similarly, for 2. So uh, for 0, there are two choices: whether you make a transition on itself or you don't make a transition on itself. For 1, again, you have
So,
two choices. Huh?
so for each number we have two choices.
Correct. Now, there's one more thing: whether your final state is, whether the start state itself is a final state or is it not a final state. So you have two choices for that as well. So this would count up to 16. In this case, in the case of DFA, you did not have a choice over 0, 1, 2, because it forces you to give you a state. So this was already fixed. Only choice you had was whether this should be a final state or it should be a non-final state. So that's why you ended up getting two DFAs only. But in this case of NFA, you have additional choice. I mean, apart from the fact that is it a final or sorry, that there is a final state or not, you also have a choice on every transition. So just for the sake of clarity, I'll draw a few possible NFAs here. So one possibility is that it doesn't yeah, it doesn't really make any transition. The other possibility is that it doesn't make a transition, but it's a final state. Then one possibility is it goes to itself on zero. Then, I mean, you can see, right, what the pattern is. It, yeah. Oh, so are there any questions? I didn't draw all of them because 16 would be possibly taking.
Yes, understood, ma'am.
Correct. So I think I had a few more questions, but since it's already 8 o'clock, maybe we can take it up next week. But if there are any questions or about whatever we did today, you can ask me right now.
Miss, like I have questions for the previous topics. Can I ask now?
Okay, in that case, maybe I'll stop the recording because, okay. But others, if there are no questions, I mean, feel free to leave. And yeah, thank you. Thank you for attending. And I hope this is helpful for you. Okay, so what I'll do is I'll stop the recording, then I'll wait for 5 minutes.